Hello everyone, this is a video lecture for Calculus 1, Chapter 5, Section 5, U substitution. This is what you've been waiting for. And I'm sorry to say that this is also the very end of Chapter 5. It took them this long to get to what I would call the meat and taters of what integration is all about. This you'll carry on with you into Calculus 2. This you will carry on with you into everything you're doing, calculus-wise. Okay? This is very important. You skip all the other stuff before this, fine. This is what you need. And it's a big section, too. There's a lot of content here. I'm going to try to show you as much of the depth and the richness as possible. So, here we go. I have in my notes there, it says the best way to do it is just to do it. And so I really will just be starting with a homework problem. This is definitely a classic. It functions perfectly for what we're wanting to do. And it's actually pretty easy at the same time. So I really like this problem. So U substitution. Here's the thing. I want to find something that's typically on the inside where there will be the derivative of that on the outside. Now, I don't know if I would write all that down. That's not a gold statement. That's nothing, really tried and true. But complicated insides for sure are a good start. So I'm going to say complicated insides. They're really a good place to start. And so in this case, can you see it? X cubed plus 7. Now, the funny thing with this particular problem on the homework is that this was given to you. They said, hey, this is what U is. Go ahead and find it out. And I'm happy that they did that. That's okay. But they will not always do that. In fact, I don't think they do that hardly any more times. Anyways, I'm looking ahead. I don't see it come up like that anymore. You've got to find the U. So keep that in mind. It's kind of like complicated inside, but sometimes it's not just that. There's a lot to this, okay? So we have this U. What I want to do is now find the derivative. And so then that's a du. I'm finding the derivative not like u prime, but I'm finding the derivative du. I'm doing this implicitly. This is an implicit differentiation stuff. And I know that you might not have good memories of that implicit stuff. I honestly love it. But at the same time, don't overthink it. It's truly not as implicit as it sounds. The 3 comes down, and you leave a 2 behind. The 7 goes to a 0. And this whole thing here is times dx. Why a dx? Because it's a derivative. It's a flag. I'm saying, hey, guess what, guys? I just took a derivative from u to du, from x's to dx. It's a flag. Okay? Very important to have that. I'm going to get rid of my flags. You don't need my flags. Okay, so this is a very vital step. And I'm going to say that most professors, most teachers, probably the book, because I don't read the book, probably the book, they all stop there. They say, okay, well, there you go. Now, just go ahead and figure out the rest of the problem. You got this. I gave you a thumbs up, but you couldn't see it. Here's the thing. This is good, but there's better. Okay, so what I'm going to do is now I'm going to solve for dx. I want dx equals, okay? And so in order to do that, I'm going to take all this and divide it to the other side, like this. What I'm going to do with this problem is I'm going to use my u and my dx. And all I'm going to do with these guys is I'm going to plug them in directly. Some teachers cannot do this. Not that they can't do that. They refuse to have this happen. This is not a good way to do math, etc., etc., etc. I have found it incredibly handy. I used to try and do it the proper way, and I did not get very good grades when doing it. And then I discovered this little trick. It's so simple trick. And, like, everything turned around. It was so much better. So you don't have to do it if you're a proper person. Mixing up variables is no fun, but whatever. So all this right here is a u. And you see the dx. I'm just going to replace it right here with du over 3x squared, okay? So that's literally a copy-paste. Now, this is where they have the problem, a lot of teachers and other folks. They say, oh, well, you can't have both x's and u's mixed up. I don't care. I mean, it's just a formula thing. And the purpose behind this u substitution stuff is that the x's just cancel anyways. And so we would get the same thing in the end. So no hard feelings, okay? No hard feelings. Just do what you got to do. I like this method better. I found, sadly, that as I move on into Cal2 and Cal3, I often don't do that method anymore. On the recordings, I might or might not. I can't really remember. But in class, I've just been not doing it at all, and everyone's okay because I guess in a way it's kind of like the training wheels. You don't have to have the training wheels on all the time, but if you want to keep them, that's fine too. There's no problems there. And so that square root u is actually a 1/2 u. Notice that everything's a u now, and that makes it easier. So I'm going to go ahead and add 1 to the power and divide by the new power. Is there a definite here? No? Okay, plus c. That's great. I'm going to take this and flip it up. And so then we got 1/3 times 2 over 3 times u to the 3/2. And the 3's combine to make 2 over 9. U to the 3/2. Oh, I forgot a plus c here. All right. There you go. We did it. Well, yeah, but we got one more step. We have to plug back in my u. Remember, u was equal to this stuff right here. And so wherever you have a u, you now go back and put the x cubed plus 7. So now to the 3/2 plus c, and there you go. Final answer for sure. Okay. There is a few things that you'll have to remember to do this properly. But in the end, this is something that you will, not that you could, that you will be using on a day-to-day basis, literally a daily basis, as we keep going. Very important thing. So let's keep going. Got a lot of examples, lots of fun stuff up ahead. I got a 4x plus 3 in the denominator. And they got that dx in the top. That often scares me. I like to put a 1 and then a dx right here on the side. That's just me. But you know what? I'll do whatever they say. So what's the complicated inside? Yeah, let's just use the whole denominator. So then du is going to be a 4dx. Notice, that one's easy. I said the 4 stays, the x goes to a dx, right? Implicit flags, the 3 goes away entirely. I'm going to solve for dx. That's going to be a du divided by 4. Notice all I'm doing is dividing that to the other side. I'm going to use these two right here. And so then I can replace that dx on the top with a du over 4. And then the bottom is just going to be a u. Well, that 1/4 can actually come to the front to make du over u. And pause. And pause. Okay, what's that integral? Come on, help me out here. Yeah, I know. You probably don't know it. I'm going to go ahead and give it to you, okay? So integral of 1 over x dx is equal to ln of x plus c. There's a lot more behind this than what just meets the eye. So if I said, well, what's the derivative of ln of x? And you would say 1 over x, 1 over stuff, right? And the chain rule and all that other stuff if you need to. And that's good. We like this. That was fun back in the day. Now we're going to step it up and go the other direction, and we get ln x. But you see these absolute value signs? They are absolutely required. And so, yes, you definitely need those absolute value signs if you're going to be getting it right, okay? So there's your formula. So guess what you're going to have for your actual answer? The 1/4 is in the front, ln of u. Okay? Plus c, I believe, right? Yeah. And, of course, we cannot leave it with a u. It's got to be the 4x plus 3. And there you go. There's your answer. Now we're done. These are fun problems. Integral of ln of x to the 10th power divided by x dx is equal to what? Again, this is one of those, woo, look at that guy. I really like these kind of problems. Notice that the lnx does not have absolute value signs, and that's okay. If they don't provide them, that's on them. Just let them do whatever they want. You must be using those absolute value signs if it comes down to one of these integrals here, okay? So just watch out. So what would be my complicated inside? I'll wait for it. X? Did you say the denominator? No, you didn't. Just note for a second here. Here, just let me just pause. What if you did say the denominator? I mean, it is an inside, I guess. It's not as complicated as some other things, but it is something to consider. Well, du is equal to dx, and all you've done is just traded letters. You didn't actually do any work here. This didn't help you. Okay? You would be stuck. It wouldn't have changed anything. And so don't go down that road. Not now, at least. Notice, yes, it's the ln x. He's on the inside. And so my derivative of ln x is 1 over x dx. Remember, not absolute value signs this way. It's the other way. It's the backward stuff. And I want to solve for dx. And so I'm going to actually multiply the x to the other side, so it's x times du. And I can plug it in directly. So then I've got my u to the 10th divided by x, and then times x du. And again, the purpose of that is so that your x's cancel properly, so that you're not actually messing something up. Add 1 to the power. Divide by that new power. Replace that u with exactly what you had. What was your u? It was not an absolute value, blah, blah, blah. It was ln x just as it was. So put in the ln x just as it was, okay? Let them figure it out. That's what they started with? Fine. All right. Keep going. 55027. So I've got integral of secant squared theta times tangent cube theta d theta. And this is a classic problem. This is something that you would find in Cal 2 for sure. I mean, I remember doing this just a couple days ago in my Cal 2 class. So I have a note here. It says, this one is a hard one. Which do I use as u? And then I say, let's just try something. Oh my gosh. So I turned a page, and I have the whole page filled up with this problem. And then it's actually on the back side of the page. Oh my gosh. This thing goes on for 2 whole pages. I'm not exaggerating here. It's a very good problem. Very classic problem. All right, so buckle in. Here we go. Which one do you want to use as u? Do you want your secant or your tangent or something else? I'm going to use secant. I don't know why. I'm just feeling like it's secant today. And so and it's really, you just pick whatever one you want and just start rolling with it. As I say, maybe other times, is that if you're going down a road and it doesn't look like it's going well, turn around, don't drown. Just seriously, don't. If you tried tangent and you didn't like it, just try secant. If you're doing the secant with me and you don't like it, try the tangent. If you don't like either of those, skip. No, I'm playing. Is he serious? So what's the derivative of secant? Is secant tangent d theta, and I am going to solve for d theta. I know it's a simple step. You probably have figured out how to start canceling things at this point, but it's very nice to have that handy and around. So that's going to be a u squared. That's tangent squared, u squared. I have a tangent cubed, which I don't know what to do with. And then I have this du over secant tangent. You know what's interesting is that right now, one of these tangents will cancel with that. So I got u squared over secant theta times tangent squared theta du. So this is all mixed up. Oh, you know what? U is secant. So I could just replace that with a u right there. But I still feel I'm lacking something here. Let's just cancel. I'm still lacking something. It's still not quite there because I still have this tangent squared business. It's a du. Don't mix that up. There's a formula for this one. Going way, way back, we have tangent squared theta plus 1 is equal to secant squared theta. And so using that formula, you can actually just move the 1 over, and it would be a u and then secant squared theta minus 1 du. What's interesting here is that that's a u. That's u squared minus 1. Distribute. So then we got u cubed minus u du. And that is nice. And so then we got u to the 4th over 4 minus u squared over 2 plus c. Replace all your u's with secants. And we're done. Well, that was not nearly as bad as I thought it was. You want to know why it's bad? That's good. It's good. We're done. We're seriously done. That's it. WebAssign they have tangent to the 4th power of theta all divided by 4 plus c. That's their answer. All right. Let's have a small discussion about this for a second, okay? Oh, I see. Let's have a small discussion here. Do you need to type in what WebAssign says is right? I mean, you could if you want, but they don't need it like that. This right here is legitimate. Okay, we're fine. There's nothing wrong with what we just did. If they do say that that is wrong for some reason, you send me a message. Do the Ask My Teacher. Okay, I want to see. I want to look and see if it really is equivalent, or I mean, it could be a technical issue. You never know. On the WebAssign side. What I want to do is try to get to that. Somehow they simplified and they got to this answer right here from this. How in the world is that going to happen? And that's what is taking up most of my room here on the page. And so I want to do this with you just to kind of chillax with you. Okay, so set the pen down, just ×2 speed or whatever, and let's just try to figure this thing out. I'm going to factor out a common factor here, and that's going to be a secant squared over 2. And please forgive me for not actually using thetas all the way, okay? They would just be too long. You don't want that. That's supposed to be squares. I don't know why I put it so weirdly. I mean, I'm a lazy guy, but I mean, come on. So I did that, and what I'm going to do is factor out... actually, no, I'm going to change these secants into tangents. I think that's probably the safest bet right now. So that's going to be a tangent squared plus 1, and that's going to be a 1/2 tangent squared, and then plus 1, but then minus 1, right? Because the minus 1 is still there. And these guys cancel, so that's nice. The halves can actually now come to the front, and so I would get a 1/4. Oh, I'm doing this way different on my paper. A 1/4, and then you could distribute this guy in here. So we got tangent to the 4th plus tangent squared. I really feel like I'd mess something up. Just hold on. Let me just give me a second here. I see it. I did mess something up. Pause. Back up. I knew I was messing something up. Did you see it? Where was it? Where was the mistake? That 1/2 is right here, like that. Distribute the half first. Oh, man. I didn't see that. Maybe you did see that. I don't know. I didn't see that. And I have my notes, like, right in front of me. Right here. I might not do the plus C every time just because I'm lazy today. That's a -1/2 now, because those combine to make a -1/2. All right. That's cool. I guess. I guess we could distribute. We could FOIL this thing out. Doesn't that sound like fun? Let's do it. Let's do it. So then I'm going to start foiling this thing out. We got a 1/2 in the front. And so I'm going to have here 1/2 tangent, actually to the 4th. And then we got a minus 1/2 tangent squared. We have a positive 1/2 tangent squared. Oh, that's kind of nice. And then we got a minus 1/2. Well, those guys goes away. That's nice. Let's go ahead and factor that back in. Foil factor? I don't know. Anyways, so we got tangent to the 4th. I'll put a theta this time over 4 minus 1/4 plus c. Remember how our answer was supposed to be, right? This guy? So we're off by a little bit. That guy's not supposed to be there. And you know what's funny? Is that you could actually just get rid of him. How? How can I do that? It's not good math. Well, what's going on is that this C here is ambiguous. It's just C, and what I say is that it absorbs, like a sponge, anything that's a constant around it. And so that C, this is C1, now this will be a C2, blah, blah, blah. But in the end, it doesn't really matter. So this is tangent to the 4th over 4, and now plus C. It's a different C. These are not the same C, but I wasn't really using that other C to solve for anything anyways. So it's C. We did it. Yeah, it took forever. Here's a new way. What if I had originally said, and let's start back over with my original integral. Flipping the page. Oh my goodness, it's like on a whole other page here. Hold on. Oh, here we go. Secant squared theta, tangent cube theta d theta. So what if, instead of going through all that long road, what if I had done u is equal to tangent at the very beginning? Like right here. Like did the other side. What if I had done that? Well, let me just kind of skip a few steps here. The secant squared is tangent squared plus 1. And then this tangent here is going to be our friend here in just a second. So we got a u, got a du. What's the derivative of tangent? Is secant squared. Oh, I don't like what I did. Here, back up, back up, back up. No, I don't like it. Let's just do it right here. I'm not into video editing, can you tell? So my d theta is going to be a du over secant squared theta. And so I can actually rewrite this now as saying secant squared u cubed and then du over secant squared. The secant squares cancel. And we're left with this guy. Add 1 to the power, divide by the new power. And that the whole time was a tangent. And there you go. We did the entire problem in like 3 steps. Gosh, man, why didn't we just do that? Why didn't you just tell me that step? Why didn't you just do the tangent at first? Well, because. Did you know to do the tangent at first? I didn't. I didn't know which side would have been easier. So it's okay to go down different roads. You'll eventually get there. It's a learning lesson that you can do different styles and different U's and you'll still be okay. You'll still be okay. Do whatever feels comfortable to you. Okay? Now this one is strange. Ooh, it's strange. Look at that guy. So I'm supposed to figure out now what my U sub is. So U is going to be equal to the complicated inside. Of course. Of course. So my derivative then, the negative 11 actually comes down. And now I subtract 1 from the power. So now it's a negative 12 dx. And so I got dx is equal to du divided by all the stuff. Now, I can make that look a lot better. I'm going to say that this actually is in the numerator. Leave that in the denominator. He's fine. So I'll use these two now. I'll just plug them in directly. So cosine of u over x to the 12th. Whoa. X to the 12th du divided by a negative 11 pi. And those guys cancel. The 1 over negative 11 pi can come to the front. What's your integral cosine? It's a positive sign. Replace your u with the x's and stuff. This stuff here. So that would be the pi over x to the 11. And then plus c. That's it. You're done. So, all right. I like to do a lot of examples here because, I mean, honestly, it's just the last section, and I wish there were about 5 sections devoted to this stuff, because this is the real stuff here. This is the real integration. Okay. Here's another one. Look at that. Honestly, that stuff is tough. What do we do? So we got to pick a u that would make the most sense. And there's definitely different answers to this. This is hilarious. It's up to you about what you want to do, though. Yeah, I like this style. Let's just do the whole denominator. Let's just do it. All right. So I've got 2 cosine of... Okay, yeah, let's do some chain rule. This has been a while. I know that y'all know the chain rule stuff, but it's been a while. So the 2 comes down to... This is a 0. 2 comes down to the front. Leave the cosine alone. And then now it's a 1 power. And then you take the derivative of the inside. So the negative sine of x. And then a dx. And then I'm going to solve, of course. It's negative 2 cosine x sine x. Do y'all see something? Do you see something? This right here. I'll put the negative in the top. That thing right there is sine of 2x. Oh, wow. So then when I integrate, I actually got sine of the 2x divided by u, and then I've got negative du divided by sine of 2x. And these guys cancel. Leave behind a negative in the front, 1 over u du. Do you remember that integral? It's ln x. Whoa, it's ln u in this case. With the absolute value signs. Very important here. Plus c, of course. Why do I have 2 equals? I don't really know. Moving on. And so then we need to replace that u with a 9 plus cosine squared theta. No, it's x. Gosh, man, I keep messing that up. X. And then we got the plus c, and there you go. Now, WebAssign does not have this answer. No, it does not. It has this answer here. Because they're sophisticated. Didn't you know that 9 plus cosine squared is always a positive? Yes. Okay. This still works. It still works, okay? They're just being a little too particular. They don't wear glasses. They wear like a monocle. And they twirl their mustache. So 55047. I've got integral of cotangent of 10x dx. I mean, this is like so classic right here. Come on. Figure it out. Is there a formula for this? Gosh, there must be a formula for this guy. Kinda. Now, there is a formula, and you can get that formula done very quickly. I tried to do that on my work. You can't see it. I would hold it up and show you, but there's a huge X. I mean, like, not solve for X, but like I crossed through so much work. I had to scratch through it because I messed up. I went and tried one style, and it did not work in the end because I forgot some formulas. I recommend going the long road here, and it's okay. That's better than getting it wrong. So I'm going to say rewrite this thing as cosine over sine. And I'm going to choose a u from the bottom. And the reason why is because I decided to do that. You might have been able to do the cosine. It probably might have worked. I don't know. But if I do the bottom, I think it cancels with the top a little bit more often than not. And so when I take a derivative, I have to multiply by the 10 dx. And so dx is equal to du over 10 cosine of 10x. So I'm going to plug these in directly. I got integral of cosine of 10x all over u, and then I've got du over 10 cosine of 10x. Cancel, cancel. The 1/10 can come to the front. 1 over u du. Have you seen that one before? It's an ln. Oh my goodness. And so then replace that u, of course, with sine of the 10x. Oops. There we go. Plus c. And that's it. You're done with that problem. Cool. I don't know what else to say. Do it like that. Absolute value sign is definitely required here for sure. 55050. I got integral of x cubed over 1 plus x to the 8th dx. This is a very good one. Okay. Now I'm going. Sometimes I mess up on purpose, but I don't tell you, and you think, "Oh man, he's not doing it right." I'm going to tell you, I'm going to mess up on purpose. Okay, and it's important to see these mess ups. I think that we learn best through mistakes. And so it's okay to make a mistake so that you don't do it again. That's at least the idea here. And so what if I just chose the entire denominator? And so what I would get here, derivative-wise, is a 7th power. Oops. Hold on. Something kind of like that. Plugging it in, I got the cube from the top, I got a u from the bottom, a du, and then an 8, and then an x to the 7th. You can cancel a lot of these, and the 1/8 can come to the front. But in the end, I'm stuck with x to the 4th, not a dx. Do with this guy. What are you doing? So then you stop. You go and do something else. I'm serious. When you see this kind of thing happen, turn around, don't drown. Try something else. So it wasn't u equal to that thing. Let me rewrite it. And this is going to be a silly thing, but this is very important for your future. This is for your future. Right here. Pause. Do you see what I just did? I made that 8 into a x to the 4th squared. What I'm doing here is I'm looking ahead. I'm saying, hey, if this is my u, what's my derivative going to be? X cubed. I mean, with some more numbers, of course, but I mean, that's basically going to be my du business, okay? So I'm looking ahead, and that way I can say just this guy, just that guy, nothing else crazy here, 4x cubed dx, so dx is equal to du over 4x cubed. And so I can rewrite it now as x cubed, 1 plus u squared, du over 4x cubed. And these guys cancel entirely. The 1/4 comes to the front. And have you seen this integral before? Yes, 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 you have. Yes, you have. It's arctangent. That's it. Oh, plus c, of course. We need to replace our u with whatever u was, and now it's x to the 4th. And there we go. So I have a little note here that says, look ahead for the du. The book promotes that method much more than me. And it is a good thing to promote, but I don't think that you need to do it every single time. It's just something that is a good thing to look ahead for when you're really stuck, okay? And remember, I tried a different style. It didn't work, so now I'm stuck. What should I do? Well, look ahead a little bit, okay? It's I don't necessarily do that in the first place every time, especially in Cal 1, maybe in Cal 2. Okay. This integral here is actually interesting. It's different than what we've done before. Do you want to know why? It's because it's a definite integral. We haven't yet done one of those with a u sub yet, and that's okay. Now, I can see ahead. I can see ahead how and to get all this, but I don't want to do all that with you right now. I want to focus instead just, on the basics of the definite integral stuff. Well, the 3 is going to come out. And so then we got the pi over 2 t dt, and we're still going to have to figure. Okay, so where was I? So sorry, sometimes things happen. So the 3 comes out, we got a cosine, and just basically I'm just going to zoom ahead here. My integral of the cosine is going to end up being a sine. I could just basically see that ahead of time. But we have this pi over 2 business inside here, and that's not really, it's not just a copy paste. We have to do some math here. I would love to show you the quick version, but I think it would draw away focus from what I really want to show you here with this definite integral problem. Okay, so now I'm back on track now. I want to do a u sub with the inside, the complicated inside, okay? I will, like me, Chad, will not be doing this very often because it's way too easy to do the quick method, okay? I'm just trying to show you the long method once or twice, okay? And so then we got a du divided by pi over 2, and that's fine, whatever. And so 3 integral of cosine of u, and then I have my du divided by pi over 2. And this guy can come out to the front. And so that's actually going to be a 2 over pi times the 3. And then cosine of u du. And that's a 6 over pi, essentially. Oh, the pi kind of looked like a division symbol anyways. Okay, now, I've been missing something, my definite integrals. And I would say traditionally you do not need to write those. Do not. I mean, what I'm going to do here is just for silliness sake, but you do not have to write those every single time. But what you do need to do is know what they are, okay? So you can't forget them. I'm going to do this on purpose. So at this point, we're talking du's now, no longer dt's. These are t values. I don't want to mess this up later. And so I'm going to say that this is t equals 0 to t equals 1. Now, could you do that over here? Yeah, I mean, sure. That's like a duh. Duh, it's t right there, man. Right, you don't have to do it right there. But I'm doing it here because we don't have t values anymore. Again, this is one of those moments that most teachers are like, "Ugh, I cannot believe you're mixing up those variables. What are you doing?" And I know. I'm just going to do my own thing. That's just what I do. And that's okay. Some people do the mixed variables sometimes. So I'm just kind of hanging out and reminding myself, those are t values. Those are not 0 to 1. I would say if you were to just do integral 0 to 1 at this moment, blah, 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 du, that is wrong. That is clearly wrong. It's not you being lazy. It's you being wrong. So don't do it, okay? Either don't put them at all or go ahead and put your t equals. I'm very serious. Okay. So... Oh, well, we should probably just take the integral. What's your integral of cosine is going to be a sine, a plain old positive sine. Again, from t equals 0 to t equals 1. Very, very, very important to remind yourself about what's going on. Now, I can replace that u with my t stuff now, right? Pi over 2, t. Now you can go back to the 0 and 1. Now it's okay to do that, okay? Again, if you did not have the t equals right here and you're being lazy, that is very wrong. That is very wrong. Do not do that. I mean, if you really don't like it, just don't put anything. Just put a big line, and it's fine. Okay. Now, plugging in the 1, plug in the 0. Here we go. we get pi over 2 times the 1. And then anything times 0 is going to be a 0. But what is sine of 0 is 0. And sine of pi over 2 is a 1. And so there's your answer. I guess you could just simplify a tiny bit more. Yay! All right. So I have a little note here. It says, notice how I wrote the limits so that I don't mess up. Don't plug in for u, instead only for x. That's just me reiterating what I was saying. Why did I say x when I should have been a t? Whatever. That's fine. No problem there. I would love to show you the quick method, but I'm not going to do that. Not because of time's sake or anything, but because it would take away from the core of that integral. It's like a learning lesson here. Same thing with this guy. So I'm going to choose the complicated inside, and du would be, well, dx. This should not worry you. Normally it would, but because you got something more than just a plain old x, it actually is okay. And so let me go ahead and plug this thing in. I got an x equals 3 to an x equals 4 of x square root of u du. I'm lost. How do I get rid of that x right here? How do I get rid of this guy? How can I cancel them? Normally they just cancel. You see something? Right here, I got u is equal to x minus 3. What if I add 3 to both sides? And so then x is equal to u plus 3. And then what you could do is simply say, again, I was going to be either lazy or very particular. Nothing in the middle. I'm going to replace that x with this. This happens sometimes, and that's a good thing. This is a good problem. I love seeing all the different techniques that we're supposed to be using with u sub. And here's the rest of the problem. Distribute that square root u, and so you got u square root u plus 3 square root u du. And that's going to make a u to the 3 halves plus 3 u to the 1 half du. Very particular about parentheses. Add 1 to the power, divide by the new power. That's supposed to be a plus sign. 3 halves, 3 halves. And then plus c? No. This is from x equals 3 to x equals 4. Do not plug it in directly into u. Do not. These actually, they're going to cancel the 3's and a 2 comes up as a numerator thing. You could just put a win bar if you're tired of it. I mean, I'm serious. There are ways to make this simpler, more simple. My u is this guy, so just plug that in directly, x minus 3. There are ways to make this easier on the eyes and quicker to write, just as long as you're doing it properly, okay? I can't give you every single specification of what is actually right and wrong with shorthand math, but parentheses are good. Let's just start with that. And if you want to go a little extra, it's better than nothing. Plug in the 4, plug in the 3. If you plug a 3 in, what happens? It cancels, makes a 0. When you plug in a 4, what happens? They turn into 1s. And so the fast version here is this right here. And you do the math, and it turns out to be 12 over 5. There you go. I have literally one last problem in this entire chapter. Capital R of t is equal to 65 minus 0.18 cosine of pi t over 12. And they want to say, what's the integral from 0 to 24 of r of t dt? Now, I think this is a word problem. I just haven't really looked at it. I want to utilize this time together, this last problem, to give you a quick trick. A quick trick as to figuring out these integrals. Why is it on the last problem? Why couldn't you have shown me earlier? It doesn't apply every time, honestly. It just applies sometimes. And in this particular case, This is your u, isn't it? And so here's how you do it. Instead of going through all the u process and stuff like that, what you want to do is you're going to divide by the derivative of the inside. You're going to divide by the derivative of the inside. It's actually so unofficial that I'm not going to even write it down. You need to hear me. I'm not going to write it down. You're going to divide by the derivative of the inside. Right here, this is the inside. What's the derivative of this? Well, it's this guy. But I'm going to divide by that. Okay? And so your answer, this one's super easy. It's just a 65, what, t? T, yeah. And then we got a 0.18, and then I'm going to divide by this. Or rather, you can just flip it. And then my cosine turns into a sine directly. Leave the inside alone. And from 0 to 24. Now, I did a lot of crazy math in the middle there. Did you see all that crazy math here? So how is it that I could divide by this? See, and I flipped it. Maybe I should have just showed you 1 over pi over 12. That's either way is fine. But why am I dividing by that? Well, it's kind of like chain rule. Let's go back and say we had the sine of pi over 12t, and I want to take a derivative of this thing. And so your sine goes to a cosine. You leave the inside alone. You take the derivative of the inside, like that. And see how you're multiplying by the derivative of the inside? That's for a derivative. You're multiplying by the derivative of the inside. That's your derivative stuff. It's a chain rule. But the anti-chain rule, I guess you could say, is not multiply, but divide. Divide, okay? So we're dividing by that value instead. And here in this case, it just flips the fraction. Plugging in the 24, we get stuff. But when you plug in a 0, you'll get 0 and sine of 0, 0. So you don't have to do that one at all, thankfully. 65 times the 24 minus 0.18, 12 over pi, sine of the pi over 12 times 24. That's going to be pi over 2, makes a 1, by the way. And why did I... Oh, no, never mind. It's not pi over 2. Hold up. 24 over this makes a 2 pi, right? That makes a 2 pi right there. Sine of 2 pi is a 0, so all this goes away. Leave behind only this right here, the 1560, and you're done. And we're done with Chapter 5, finally. It has been a wild ride. I got to say, this Chapter 5, it was not in the format that I wished. And I'm sorry, but I'm very thankful for all the wonderful questions here in the last 2 sections in particular. Those were awesome. Those were very good, and you honestly should practice 3 times as many as these, because this is something very, very, very important to your future as you keep moving. All right. That's all I got. Thank you very much, and have a great